It's a pleasure to present Pablo Carrasco. He is the third speaker of our session. Pablo obtained his PhD at the University of Toronto under the advice of Charles Pugh and Mike Chu. He has postdoctoral positions at IMPA, at UFMG in San Carlos, and at Penn State. And at the moment is a professor at University Federal of Minas Gerais, a colleague of me. It's a pleasure to present you. And Pablo is going to talk about unique ergodicity of quasi-invariant measures for time-one maps of hyperbolic flows. Thank you, Pablo.
All right. Thank you, Karina, for the kind presentation. And let me thank also the organizers for the invitation. It's a pleasure to be here with you today. The title is the one that you see in the screen. It's a kind of long title, but anyways, I'll give you the outline of my talk. I'm going to start telling you about these new results on well-known systems. This is an introduction. Then I'll move to discuss quasi-invariant measures for the Oro-cyclic flow. After that, I'm going to talk about equilibrium states for Anoso flows. In the end, I'm going to give you some ideas of the proof, and I'll try to conclude with some open questions and general remarks. Now, my talk is about some very well-known systems, these being hyperbolic flows or Anoso flows. Now, what we are going to do is I'm going to present some new pieces in the ergodic theory of hyperbolic flows that relate thermodynamic formalism with the topological properties of their invariant foliations. Now, the ergodic theory of hyperbolic flows is probably one of the most successful pieces in smooth ergodic theory, and we know a lot about the statistical property of such systems. In any case, I'm going to tell you today about this result that show that there is still some room to to research in this part of the theory. All things that I'm going to say are joint work with Federico Rodriguez-Hartz. They are part of a larger project where we are interested in understanding regular elements of general Anoso functions. But for today, the only thing that I'm going to focus is on hyperbolic flow, that is rank 1 Anoso functions. I'm going to be honest with you. I'm going to assume that all of you know what a hyperbolic flow is. These type of systems are usually covered in basic courses. So instead, I'm going to give you one slide definition of the type of properties that I'm going to be using, and such. The only thing that I'm going to do is I'm going to fix some notation. By an hyperbolic flow, I mean a C2 flow. I'm going to do ergodic theory, so I'm going to use the C2 hypothesis, which I'm going to denote like this. Phi is from M to M. M is a closed Riemannian manifold, compact without boundary, and such that there exist foliations, the unstable, the center, the stable, the center stable, and the center unstable foliations, which satisfy the following properties. First, they are flow invariant. If you take a leaf of one such foliation and you apply the dynamics, you end up in another leaf of the same foliation in the corresponding point. This center foliation is the foliation by orbits. It's a C2 foliation, differentiable foliation. And the center and the unstable subfoliate the center unstable. It means that if you pick a center unstable leaf, it's union of orbits, and it's also union of unstables. And the same happens for the center stable with respect to the center and the stables. These foliations are transverse in some sense, are very locally transverse, and I'm going to say this in the following way. There is some constant, which I denoted by CGO, such that for every x, you can use the foliations to build a coordinate systems around x in the manifold. So there is a foliation preserving coordinate system. Well, this is my notation, WUXZG. That means that this is the unstable disk centered at X of radius CGO, whatever I'm writing there. And for example, here you can use C and S to define a coordinate system and local coordinate system around X in the center stable leaf. And then you use this with the unstable foliation to build a coordinate system in the whole manifold around X, of course. And finally, I'm going to use need the hyperbolicity condition. Is the flow exponentially contracts or expands distances, intrinsic distances in the stable or unstable leaves, and the rate is lambda or 1 over lambda correspondingly, where lambda is a number between 0 and 1. Okay. Now, I'm going to assume that my flow is topologically mixing. This is not really a big deal. Essentially, you have the following. If you have an hyperbolic flow, well, it is transitive or not, okay? So I'm going to assume that it's transitive. And if it is transitive, there are two possibilities. Either it is the suspension of an awesome map, or it is topologically mixing. So I'm going to assume that it is topologically mixing. You can be more general here using the spectrum decomposition, but anyways, this is going to be our hypothesis. And what's an example? Probably most famous and most important example of all this is a geodesic flow corresponding to a closed hyperbolic manifold. There, the flow acts in the unit tangent bundle of the manifold. So this is the M is T1 of S. S is the hyperbolic flow. However, most hyperbolic flows are not of this type. And even if nearby this important geometrical example, you can find hyperbolic flows that are not geodesic flows. For this, I mean the following, something also very well known. If you look at the vector field generating the geodesic flow, you make a C1 perturbation for this vector field, you end up with a small C1 perturbation, you end up with a vector field which correspond to an hyperbolic flow, but in general is not a geodesic flow. So even if you are interested in the geodesic flows, you have to consider more general cases. Okay. And in this talk, I'm going to be interested in the dynamics of the foliation, the unstable foliation. For this, I'm going to assume two things. First, I'm going to assume that the dimension of the foliation is 1. The unstable foliation is 1. This is what is called the codimension 1 case. And I'm going to assume that the foliation is orientable. Modulo double cover, this is not even an hypothesis, but let's fix this to work. And what do we get with this? That the leaves of the unstable foliation are the orbits of a flow, which I'm going to denote like this, which is the holocyclic flow. You could think in more general situations where the dimension of the unstable is arbitrary, has arbitrary codimension, but in this talk, I'm going to look at this as a flow. It's going, okay? So what about holocyclic flows? Well, the holocyclic flow is a prototype of what is called a parabolic flow, which I'm not going to define precisely. Let me just say that the dynamics of such systems have several consequences, for example, in geometry or number theory. Well, you know an example, probably everybody knows several examples, actually. The most simple, the easiest example is the linear flow in the torus, linear rational flow in the torus. And you see, depending on the angle, so the properties of flow depends a little on what are the numerical properties of the angle. So you have this kind of, well, some idea that it will be, there is some number theory there include. If you want to be more general, the whole Radner theory deals with this type of flows. And so there's a lot of research for that. So I'm not going to go there, But let me just say one of the most important results for autocyclic flows, which is the theorem of Furstenberg and Marcus. It says the following. It says that the autocyclic flow in the hypothesis that I'm working is uniquely ergodic. That means that there exists one and only one probability measure which is invariant for the autocyclic flow. And with this, you get that every orbit of the flow is not only dense, which is equidistributed. Okay, so the equidistribution is related to frequencies, and there again you see that there is some number theory behind all this. Okay? The Furstenberg proved this theorem originally for the geodesic flows in hyperbolic surfaces of constant negative curvature. Marcus proved this in general for autocyclic, for arbitrary autocyclic flows, and then there is a more general version to Marcus and Bowen, but this is for foliation, so I'm not going to go there. Right. Now, with respect to invariant measures for the autocyclic flow, you cannot say much, right? There is only one, and that's it. So the thing is that when you are doing ergodic theory, you are usually not only interested in invariant measures, but also in measures which are called quasi-invariants, or they have several different names. And the idea is the following: you take your measure, you apply, you make a push forward, and you don't get the same measure, but you get something which is equivalent to the original one. Okay? For example, you start with the most typical case will be you have Lebesgue in a manifold, have a diffeomorphism, you make the push forward, and you get something which is equivalent to the original. Okay? So let me talk about this. So in this talk, I'm going to be concerned with more general measures, which are not necessarily invariant for this autocyclic flow. I'm going to formalize this using the notion of conformal measures. Let me give you the definition. I'm going to say that a measure mu is conformal for a flow if there exists a family of positive functions, J, which consists of functions from the manifold to the positive real numbers, which is called the Jacobian of the flow with respect to the measure, such that for every t in R, you get this equation. If you push forward with the inverse, the measure, you get JT sub mu. Okay, why the push forward? Why you make the push forward the inverse? The thing is that if you do this, these JTs are a multiplicative cocycle over the flow. But the idea is that if you push forward, you get something equivalent. Okay, so this is just a more convenient way to write it. And now the question, which we can ask, is the following. Suppose that we are given a multiplicative cocycle over the autocyclic flow. Does there exist a conformal measure with that cocycle? And once that you know that there is one, at least one, you may ask whether it's unique or not. Observe the following. If this family will consist only of the constant function equal to 1, what this equation is telling you is that this the measure is invariant. So this is precisely the Furstenberg-Marcus theorem that I was referring before. So this is a more general type of question. All right. So let me use a different approach for discussing this type of measures. Instead of measures in the whole manifold, I'm going to talk about transverse measures. Before reading the slide, let me explain you. The idea is, whenever you have a flow and you have a measure, the measure in the direction of the flow it's not very interesting. The flow in the flow direction is just an isometry of R. So the thing that is interesting, what you care about, is how this measure behaves transversally to the flow. Okay? So we are going to make precise this notion by these transfer measures. So what is a transfer measure? A transfer measure is a family of measures. So in each point, you look at a small disk. This disk is transferred to the flow, and in each one of these disks, you put a random measure, not necessarily normalized, and you consider the family. This is what I'm going to call a transverse measure. This D is what is also called a a global transversal. Of course, the only thing that it means is in each point you have a disk. And the thing is that conformal measures essentially are equivalent to quasi-invariant measures. It's the same. What you can make the same definition that we had before. Now, the previous definition said, okay, make the push forward for the flow with your measure, you obtain a function times the original one. Now what's going to happen is, okay, I have two disks. I make the push, say, push forward, push backwards, whatever of the measure in the initial disk. I end up with a measure in the another disk, and I want this new measure, the push forward of the original one, to be equivalent to the corresponding measure given by the family in the landing disk. Right? And again, all this it's the same. So this is going to be more convenient for me. So let me write the previous question in these terms. I'm going to consider the set of Helder. I'm going to assume some regularity, but okay. Let me consider the set of Helder multiplicative cocycles, which are functions from R to a positive number, which are of the form this exponential of the integral of some function. What is written here, what is written here is an additive cocycle. And if you push it a little, you can show that they are all additive cocycles. Regular additive cocycles are more or less like this. But in any case, this is a very natural class of functions to work with. And this is what I'm going to use. So these are multiplicative cocycles. And given one element there, I can use it to build a candidate for the Jacobian. So how do I do this? Okay, I'm going to consider the following family. I'm going to take points which are in the same unstable manifold, one of the other. And I'm going to define this funny looking thing, which I'm going to take a point in the center stable disk of the original point. I flow by the unstable foliation, or the autocyclic flow, until the center stable of the final point. These are these points, this and this, the original and the final. And then I use the dynamics to iterate backwards. Now, since these points are in the same unstable, when I iterate backwards, these points are converging to each other exponentially fast. This is a Helder function. You can show that this defines a well-defined map. And it also satisfies the cocycle condition. So this, with this, I built a natural type of candidate for the Jacobian. You may remember this from probably from another. When you do, for example, when you try to prove the absolute continuity of unstable foliation, so your cocycle is what you write here is the determinant of the function of the flow restricted to unstable bundle, and so you get something like this. This is more general if you want. Okay, so this is the first result. This is the uniqueness of quasi-invariant measures. So suppose that you have a codimension 1 and also flow, class C2. I'm assuming that it's not a suspension. It's transitive. And consider a multiplicative cocycle. You assume that the stable bundle is orientable. Again, this is just modulo a two-fold cover. it always holds, and you look at the autocyclic flow, then there exists one and only one transverse measure for this phi. And this new CS is the unique quasi-invariant measure which are Jacobian given by the family H that you will given this multiplicative cocycle. So this is our first theorem. I'm going to leave it in a second so you can read it. What it says that if I give you a multiplicative cocycle, you can build a unique transverse measure, which is quasi-invariant with Jacobian given exactly by the thing that you started with. So to explain this, let me make some remarks. The first thing that I want to say is that the previous theorem is known for geodesic flows. Its existence is classical theory due to Haydn, mispronouncing his name. Okay, and uniqueness is due to Babylot and Lapierre. Barbara Shapira has also a different proof using techniques of the same flavor that ours. However, I would like to point out that these proofs for geodesic flow rely a lot in the geometric properties of the geodesic flow. It use hyperbolic geometry. And you can easily tell that because if you see the papers, there are a lot of Poincaré disk and autocycles. Really depends on that you are working with the autocyclic flow. With the geodesic flow, sorry. The other remark that I want to point out is that we don't rely on symbolic dynamics. As I told you at the beginning, our interests are regular elements of a number of actions, and you don't have symbolic models. So this is, we started thinking about these hyperbolic flows because we were working in that setting. But so this is a geometrical type of proof. And the third is also something that I said before, but I want to emphasize it here and make some connections, that if H is the constant function equal to 1, then this is exactly the Furstenberg-Markov theorem, and the corresponding conformal measure is the entropy maximizing measure for the hyperbolic flow. So I'm going to look at this connection now and tell you about equilibrium states for anodes of flows. It turns out that the existence and uniqueness of quasi-invariant measures for the autocyclic flow is tightly related to the existence and uniqueness of equilibrium states for the geodesic flow. So I'm going to explore that part now. Again, I'm going to assume that you had some at least brief introduction to thermodynamic formalism. And I'm just going to fix some notation. If you have a flow, I'm going to, for a given flow, I'm going to denote by this PR sub phi m, the set of all its invariant measures. These are the measures that are invariant for every time t map of the flow. And I'm going to define the topological pressure of the system, phi bar phi, where this guy is a continuous function from the manifold to R. As using the variational principle, this quantity is going to be the supremum of the metric entropy of the time one map of the flow plus the integral of phi bar phi integrated with the measure. But the measure is not only invariant by the time one map of the flow, but it's invariant by all elements in the flow. Okay, so this is the variational principle, and you define this EQ phi bar phi as the set of measures that achieve this equality. This supremum is actually an equality, and these are what are called equilibrium states. In our setting, one can show that the equilibrium states of the flow with respect to this potential coincide, well, at least if it is phi is held up, here I should say that, you can show that this is the same as the equilibrium states of the time one map of the flow with another potential. And the potential is this, is you integrate the one that you are given in a piece of orbit of length 1. So phi tilde of x is the integral from 0 to 1 of phi tilde integrated in the piece of orbit starting with x and ending in phi of 1 of x. And this is probably one of the most well-known theorems, the smooth ergodic theorem, is the Sinai-Reuel-Bowen theorem, that says that if you are given a mixing, in fact transitive, but anyways, you are given a mixing and also flow, and you have a Helder potential, then you have one and exactly one unique, one and exactly one equilibrium state for that potential. Right, so this is the SRB theorem. This is very, very famous. And what I want to do now is I want to characterize this equilibrium states in terms of the conditional measures. I'm going to use Rocklin disintegration along unstable leaves. The point is that, as you know, unstable leaves are never, essentially never measurable with respect to a measure. And so I have to use some measurable partitions subordinated to the foliation. So I'm going to do that. So let me again write some introduce some notation. If you are given a probability in M and you are given a measurable partition in the sense of Rocklin, then you are going to say that it's increasing for the flow or the time one map. It doesn't matter. If the following happens, if almost every point, for almost every point, if you start with an atom and you apply the dynamics, what you get is union of atoms. Okay, so in some sense, it becomes larger. I'm going to say it's subordinated to the unstable foliation. If for almost every point, the atom that contains X is a subset of the unstable leaf that contains X. And I'm going to use this name. I'm going to say that this is a slide partition. If it is increasing, subordinated to the unstable leaf. And for almost every point, the atom that contains X also contains a small disk, a small neighborhood of X inside the corresponding unstable leaf. Okay. It's a theorem that this type of partitions exist. Now, again, very famous. They originally due to Sinai. Then you have the more general version to Sinai, to Strelzin and Lederer-Pierre, and they also appear in the work of Lederer-Pierre and Young. So I'm going to use these partitions to be able to disintegrate. And now, let me tell you the other theorem. The other theorem is a characterization theorem that says the following. I'm going to work in the same hypothesis that I was working before. Show and also flows, class C2, mixing, so on. Then there exists a family of measures, nu ux for each x in M, where each one of these is a radon measure in the unstable leaf of X, and this is for every point. And such that for any probability in M, and I'm not assuming that the probability is invariant or not, for any time T map, but if you take this probability and you look at the conditionals that you obtain in, say, in a slide partition, a natural partition, to be able to disintegrate, you look at the conditionals, and these conditionals are precisely the conditional measures induced by this family. So it's the measure of the atom, the measure in the atom divided by the measure of the atom. Okay. If you have that, if you know this, then your measure automatically is your unique equilibrium state. This theorem may, depending on how familiar you are with this, so it may look surprising or not. Let me make a remark. When you are disintegrating, when you're using Rocklin disintegration, you obtain the conditionals, and you also obtain the quotient measure. But here I'm not saying anything about the quotient measure. I'm saying that if the conditionals are what they have to be, some family, then your measure is the equilibrium state. Okay. So in some sense, you get the quotient measure by is already determined. And you see, this is what is going to make the connection with the uniqueness theorem that I was referring before. Okay, so the transverse measure is going to look to be as the quotient measure, and that's why they are unique. Okay, so this is the characterization theorem, and again, I'm going to be honest with you. Most of the work is improving this theorem, but since I'm not going to have the time for doing this, let me give you some brief ideas of the proof, and I'm going to focus in the following. I'm going to discuss how the previous characterization theorem implies uniqueness of quasi-invariant measures for the Oro-cycle flow. Okay, this is again, I'm going to wave my hands a little, or maybe a lot, but anyways, at least I want to try to see if I can do to give this idea. Let's start with existence. We have the following theorem: there exists a family of measures. These measures are defined in nu ux is defined in the unstable leaf of x. This is a non-atomic fully supported measure, and satisfies the following quasi-invariant relation. If you take a point and you take some t, and you push forward, backwards, backwards with the flow, the measure in the point phi t of x, you get a constant that happens to the topological pressure of the potential times t, minus a function, and the function is the integrated version of the potential that you are considering, instead of from 0 to 1, from 0 to t, the measure. Okay, this is a quasi-invariant relation. And the map x to nu x is weakly continuous. I'm not going to discuss what I mean by weakly continuity. There is some type of continuity there. This is essentially Haydn's theorem, modulo this part, which it's not written there, but you can deduce it. It's not hard to get it also. So you have this family that exists. Okay. And now I'm going to fix the time one map of the Anoso flow. I'm going to fix a Helder potential with, I'm going to look at the corresponding measures mu that this theorem gives me, and I'm going to use the potential to construct a multiplicative cocycle. Recall that the multiplicative cocycle was exponential of the integral from 0 to 1 phi of integrate phi along the orbit of t. And I'm going to also define the following function. For a point in the unstable of x, I'm going to delta u sub x of y. Remember, these 2 points are in the same unstable. I'm going to use my multiplicative cocycle, and I'm going to pre-iterate. I'm going to iterate backwards the point y and the point x. These points again are approaching exponentially fast. This is a Helder potential. This converges. So this gives you a continuous measure in the manifold, in the leaf. Sorry. And then I'm going to use these functions to construct some projective measures. So I'm going to define the following measure for x in M. I'm going to define nu u sub x as something which is equivalent to the Haydn measure, but with this round-Nikodym derivative. Before that, let me observe the following. This measure nu ux depends on x. This I didn't write it, but this measure right here, nu ux, doesn't depend on x. If you have 2 points in the same unstable leaf, the measures are the same. But this one, it does. Okay, in nu ux, this depends on the point. But it has the following properties. If you have a point in the unstable manifold, well, these 2 measures defined by a constant that depends on y and x, a positive constant, positive constant. I wrote function here. This is a constant. It's not a function. Sorry. And therefore, you can use this function to define a projective class of measures in the unstable foliage. Right? And the other thing, the most important, one of the most important maybe, is that if you pre-iterate the new f of x, well, you get a constant minus the potential, the integrated potential at the point x times the measure that you started, the other measure. Let me make the comparison with this. Here, if you push backwards, you get a function. Here, you get a constant. Okay, the measures now depend on the point, but still, they behave nicely when you apply push forward. So let me give you the following definition. I'm going to say that a family of measures in the center stable leaves is compatible with the previous system if it is quasi-invariant for the Euler-cycle flow, and the Jacobian is given by the family that you construct with the potential. This means that the Jacobian has to be what it has to be. I'm going to say I'm not going to discuss this much, but let me only point out the following. If you look at the function that you constructed before the h, x naught, y naught, and you evaluate in x, you obtain the function, this function that you are using to construct the projective measures. So there is some relation there and some computation to be done, but this is what is going on. Okay, so it's compatible if it has the right Jacobian when you push it forward with the Euler-cycle flow. And now I'm going to use these compatible measures to build a global measure on the manifold. So suppose that you are given a compatible system of measures, and what you can do is locally you can construct a measure in the manifold. You do the following: you fix one center stable disk of small size epsilon, and you integrate with respect to the measure in this disk the new ux that I defined before. So these measures depends on x. Okay, so this gives you a measure. That's not a big deal. But the point is that you can use compatibility to show that the definition doesn't depend on the chosen center stable disk. If you have two center stable disks which are nearby, you get the same value for the measure. And then it's easy to see that you can use that to construct a measure in the whole manifold. Okay? So you can assemble all these local measures into a measure, then you divide by the measure turns out to be finite, and then you divide and you normalize and you get a probability. And the other thing that you have is that there exists a compatible family. This is proven we proved this before, so I'm sweeping under the rug some things here, such that the corresponding measure is an equilibrium state for the function and the potential, integrated potential, but we know that in this case it has to be the unique equilibrium state for the flow for the flow system. And now let us finish the proof. You do the following. So suppose that you start with a quasi-invariant measure for the Euler-cycle flow, and you are given a Jacobian, a multiplicative cocycle. Then you construct the corresponding probability measure, and as explained previously, integrating with respect to the unstable measures with respect to these ones. By construction, M has conditional given by this family. Look, it's by definition. But then I can use the characterization theorem and conclude that M is a unique equilibrium state. But I know that the unique equilibrium state has some type of local product structure, and then I get the ones that I started are the measures that correspond, the new CS that correspond to the equilibrium state, and this finishes the proof. Let me just emphasize the following thing. It's very important here that the measure, I not have to check that the constructed measure is invariant. If I had to check that, it's difficult because that depends on how these guys behave if you iterate by the dynamics, the hyperbolic dynamics. I don't know that. So I'm going to finish with some questions. First, natural questions. Can this result be extended to arbitrary codimension? We are working in that, but this requires a very subtle control of the measures in the unstables. So still some work to be done. We are fighting with this. Another is, what about more general maps? As I told you, we are interested in maps related to and also functions. Maybe this holds for some more general maps. So maybe surprisingly, we know that there has to be some center, some of these maps, not all of them. We have examples where this family of unstables do not exist. So this is still there is some subtlety also there. And the last is, we haven't thought much about this, but it will be very interesting. And we probably after this, we would like to understand something. The following. What can you say? And if you can say something with these techniques in the non-compact case, for example, say abelian covers of arbitrary hyperbolic flows, as in the case of the Saric proof of the Vavilov-Toledo-Lapierre conjecture. If that makes sense to you, is for abelian covers, you also have uniqueness for the measures, quasi-invariant measures related to the cycle flow, if the base is geodesic. So thank you for your attention, and take care.
Thank you, Pablo. Is there any questions?
Maybe one comment. Right. Do you hear me?
Yes.
Yes.
Yes. Okay. So, Pablo, thank you. Maybe one advertisement for work of my students. It's 1 year he's doing, Richard Javier Becerra. So we are, after the work of my work by Jérôme Bouzy and Todd Fisher, when we treated the maximal entropy measures, which naturally, as you said, passes through this kind of conformal type measures. So Richard took the idea and developed it to construct equilibrium states. So it is for every partial hyperbolic diffeomorphism with one-dimensional center, where it is kind of discretized and also flow. I mean, flow type, like perturbation of time one map of the flow.
Perturbation time.
Yeah, exactly. So you don't have the restriction on the dimension of the stable and unstable, but definitely you need, for some of the results, you need one-dimensional center. Then you can construct these equilibrium states for any potential, Holder potential, I mean. But of course, you don't have this strong results as uniqueness that you have, well, for technical reasons. But you have some kind of uniqueness for, I mean, if you concentrate on unstable equilibrium states, if you concentrate on some stable equilibrium states, you can get also this uniqueness, but not definitely uniqueness for the equilibrium state for the whole system. But I would advertise his work. He is my PhD student. Is finishing. Thank you.
Okay. Let me then say the following: if you have a center isometry and you have some control of the potential, you can build a Helder equilibrium state.
Yes, I saw your preprint. Yes, it's nice. Yes.
The thing is now with respect to existence in the one-dimensional case, not close to a flow, you have to. I think the more interesting than existence is characterization. because you know that they exist.
Exactly. So we correct the idea is again, as previous books, is this Margulis argument of finding kind of fixed points, and the novelty is that here the potential doesn't depend on it can vary on the center, so it is any holder potential. Yeah,
right. That's in the case of flows. Okay.
Okay, if there is no more question, let's thank Pablo again. Thank you, Pablo.